And then finally, pH and alkalinity. I mentioned earlier from the stoichiometry of nitrification that nitrification consumes 7.14 milligrams per liter of alkalinity as CaCO3 per milligram of ammonia nitrified. Now, from weak acid-base chemistry of the carbonate, dissolved inorganic carbon system, we can plot the pH versus the alkalinity for various carbon dioxide, dissolved carbon dioxide concentration in the mixed liquor. And you can see that if we have a saturation concentration of carbon dioxide, it would only be a half a milligram per liter of CaCO3. That is along this line over here. If we had supersaturation of dissolved carbon dioxide, which can easily happen because the heterotrophic processes are generating CO2 the whole time, and so the carbon dioxide concentration increases above the saturation value, but the aeration system will strip out some of that CO2. But it will nevertheless still be supersaturated. So if we're working, let's say, with a carbon dioxide concentration of 2 milligrams per liter of CaCO3, if the alkalinity is 300, then the pH would be around 8. And as the alkalinity decreases, there is very little change in pH. But as soon as the alkalinity reaches about 40 milligrams per liter, suddenly the pH begins to decrease very sharply. Therefore, if my nitrification process consumes more alkalinity than I have available in the biological reactor from the influent flow and depresses the alkalinity below 40 milligrams per liter, then the pH of the reactor will decline, and that low pH will begin to reduce the maximum specific growth rate of the nitrifiers. Here is some data from the literature where the maximum specific growth rate of the nitrifiers as a fraction of the rate at a pH of 7. So if the pH is 7.2 in this case, then the maximum specific growth rate is 100%. But if the pH begins to drop, and let's say the pH is now 7 or 6.5, you can see now the pH has reduced the maximum specific growth rate to only 60% of the value it would be at a pH of 7.2. Notice also that from a pH of 7.2 to 8, there is not much decrease in the maximum specific growth rate of nitrifiers. And so the ideal pH for the reactors is between 7 and 8. But outside of that range, the maximum specific growth rate will be depressed and cause either the effluent ammonia concentration to increase if we do not change the sludge age, or at the design stage, we would have to compensate for that by increasing the sludge age, again further still, to ensure that the ammonia concentration in the effluent remains low. So, for example, if we have a wastewater treatment plant where the influent alkalinity is 200 milligrams per liter as CaCO3, and we are nitrifying 24 milligrams per liter of ammonia to nitrate, then the effluent alkalinity will be 200 minus 7.14 times 24, which is then equal to 29. So 200 minus 7.14 times 24 is 29 milligrams per liter of CaCO3 alkalinity. This is less than the approximate value of 40, so the mixed liquor pH will decrease below 7. And in order to keep the pH above 7, we would need to do one of two things. The first thing we could do is to introduce anoxic zones into the biological reactor to denitrify the nitrate and recover half of the alkalinity that we lost in the process of nitrification. And in the next lecture on denitrification, we will discuss this further. Alternatively, if we do not want to introduce anoxic zones, we would have to dose lime into the wastewater and add the alkalinity that is being lost through the nitrification process to keep the pH above 7. that concludes the section on these 6 factors that influence the maximum specific growth rate of the nitrifiers. And now we're going to look at the different ways in which nitrogen is removed from wastewater. And one of the ways is the uptake of nitrogen by their ordinary heterotrophic organisms for growth. And this is between 15 to 20% of the influent TKN, depending, of course, on the magnitude of the influent TKN and the sludge age of the system. So, the effluent TKN generally, when we have complete nitrification, is about 5% of the influent TKN. So if we have an influent TKN concentration of, let's say, 60 milligrams per liter, 5% of that 60 would be 3 milligrams of N per liter. It would be predominantly unbiodegradable organic dissolved nitrogen and very little ammonia, because the ammonia nitrification process is complete. Between 15 and 20% of the nitrogen that is in the influent to the wastewater treatment plant is removed by being absorbed into the activated sludge, into the heterotrophic activated sludge that grows in the system and is harvested with the waste activated sludge from the biological reactor. But this nitrogen concentration in the influent that satisfies the need for nitrogen for ordinary heterotrophic growth decreases with sludge age and is also lower with settled wastewater than with raw wastewater, as we discussed yesterday. And then a third thing happens, and that is the organic nitrogen that comes into the biological reactor that is biodegradable, that gets broken down and added to the pool of free and saline ammonia in the reactor. And so all that nitrogen, this approximately 75%, is nitrogen that becomes available to be nitrified and denitrified if we want to do biological nitrogen removal. Let me explain the influent wastewater characteristics now defined from the nitrogen standpoint. And we have our influent total Kaldol nitrogen. And we have our influent free and saline ammonia. I presume you already understand how we measure the influent TKN concentration and how we measure the influent free and saline ammonia concentration. But just to recap briefly, the free and saline ammonia concentration is measured by raising the pH of the sample to about 10. That changes all the saline ammonia to dissolved free ammonia, because that is just a simple weak acid-base chemistry reaction with a pK value of 9. So if the pH is greater than 9, all the ammonia will be in the unionized, dissolved gaseous form. So we add alkali to the sample, raise the pH to 10, all the ammonia changes to the dissolved ammonia form. We then blow steam through the sample, which drives the gaseous ammonia out of the liquid into the steam gaseous phase, and we condense the steam and capture the steam in a boric acid solution. Before the ammonia goes into the boric acid solution, it is purple. As the alkali from the ammonia goes into the boric acid solution, it changes color and goes green. When the steam distillation process is complete, I take the boric acid solution and now titrate it with standard acid to neutralize the ammonia that went into the boric acid solution. And the standard acid that I titrate into the sample to return it back to its purple color is the ammonia that was added. The TKN concentration, we do a digestion step first. The digestion step changes all the organically bound nitrogen, nitrogen that is part of proteins and organic compounds. They get broken down, those organic compounds, and the ammonia, or the nitrogen that is bound in those organic compounds is released as ammonia. Then I take that digested sample and I test for the ammonia concentration. And so that ammonia result is the combination of the organically bound nitrogen and the free and saline ammonia that was originally present in the sample. And so, therefore, on this diagram here, our influent TKN is the organically bound nitrogen and the free and saline ammonia. I test for the free and saline ammonia, and then the difference between the TKN and the free and saline ammonia is the organically bound nitrogen. Now, because the organically bound nitrogen has to do with organics, it fractionates in exactly the same way as the organic compounds, which we use the COD test to measure. And so, we have, therefore, we have a biodegradable dissolved organic nitrogen and an unbiodegradable dissolved organic nitrogen. We have a particulate biodegradable organic nitrogen, and we have an particulate unbiodegradable organic nitrogen. Now, in the same way as all the biodegradable organics are broken down by the heterotrophic organisms in the biological reactor, the ammonia that may be associated with those organic compounds is released into the bulk liquid as ammonia and adds to the ammonia pool that comes in with the influent wastewater. So these two components here add to the ammonia pool and increase the ammonia concentration above that for which arrives from the influent wastewater. The unbiodegradable dissolved organic nitrogen, of course, nothing can happen to that. It's unbiodegradable and dissolved, and therefore it escapes with the effluent and sets the effluent organic nitrogen concentration. This unbiodegradable particulate organic nitrogen is the nitrogen that is associated with the unbiodegradable particulate organics and simply stays as such in the biological reactor with those unbiodegradable particulate organics. And nothing happens to it except it cannot escape with the effluent. It can only get out of the reactor by being included with the waste activated sludge from the biological reactor. So this is included with the waste activated sludge. Now, this free and saline ammonia, which gets added to it, the ammonia that is released from the biodegradable organic nitrogen, some of that ammonia is taken up for growth of the ordinary heterotrophic organisms. And that which is left over is available for nitrification. Now, if there is no nitrification taking place in the activated sludge reactor, it is completely feasible that the effluent ammonia concentration is higher than the influent ammonia concentration. The reason being that the amount of ammonia that is taken up for growth by the ordinary heterotrophic organisms is less than the organic nitrogen that is released and adds to the ammonia pool. Do you see that? All right. Now, we're going to define nitrification capacity. Nitrification capacity is the concentration of nitrate per liter of influent flow that is generated by the nitrification process. And it's simply stated as the influent TKN concentration minus the concentration of nitrogen that gets built into sludge mass and becomes part of the sludge mass that I harvest via the waste flow. And so this is the nitrogen bound up in the waste activated sludge, but it is expressed per liter influent flow. So it would be, let's say, nitrogen removed via the waste flow at 100 kilograms per day, divided by the influent flow, which could be 10 megaliters per day. So this concentration becomes 10 milligrams per liter of nitrogen, equivalent in the influent flow rate that gets used up for sludge wastage. And this nitrogen concentration here, this NTE, this is the effluent TKN concentration. Now, this effluent TKN concentration is the sum of the ammonia concentration that is not nitrified, the residual ammonia concentration, and the unbiodegradable dissolved organic nitrogen that cannot change. The nitrogen concentration that I require for sludge growth is the volatile solids concentration in the biological reactor. The volume times that volatile solids concentration gives me the mass of volatile solids in the reactor. Divide that by the sludge age, gives me the mass of volatile solids that I harvest per day from the biological reactor, times the nitrogen content of the volatile solids, then gives me the mass of nitrogen, kilograms of N per day, that I am harvesting from the biological reactor, and divided by the influent flow to express that mass as a concentration equivalent in the influent flow rate. And so this NS is the nitrogen that's required for sludge production. The effluent ammonia concentration, which is part of this effluent TKN concentration, is given by this equation here, which we've seen before, and takes account of possible unaerated zones in the biological reactor. This equation also applies for completely aerobic conditions, in which case this unaerated sludge mass fraction is 0. But if I have an unaerated sludge mass fraction of, say, 40% or 0.4, then I would have to put 0.4 into this equation to calculate correctly the effluent ammonia concentration. All right. Now we're going to describe the design procedure for nitrification. And the first thing, and I want to stress that, and that's why it's in red, is that the calculation of the sludge age and the decision of what proportion of the mass of sludge in the system that must be in a non-aerated fraction is the most important decision that we are making for the biological reactor. It fixes the sludge age of the reactor, it fixes the volume of the reactor, and it will fix the cost of the reactor and secondary settling tank system. Once we've made some decision regarding the sludge age and the unaerated sludge mass fraction, then we calculate the influent nitrogen concentrations. We calculate the organic nitrogen concentration, which is the difference between our measured TKN and our measured free and saline ammonia. We calculate what the unbiodegradable dissolved organic nitrogen concentration is, and we calculate what the unbiodegradable particulate organic nitrogen concentration is. We then calculate the effluent organic nitrogen, and that would be simply the influent unbiodegradable dissolved organic nitrogen, because it flows right through the system. We then calculate this nitrogen concentration that we require for sludge production, NS. We then calculate what is the minimum sludge age for nitrification based on the maximum specific growth rate that we've selected for this particular wastewater. Now, if the sludge age of the system is less than the minimum for nitrification, then no nitrification will take place. And then the effluent nitrate concentration will be 0, and the effluent ammonia concentration will be the influent TKN concentration minus that amount of ammonia that is required for sludge growth, minus the unbiodegradable dissolved organic nitrogen. This ammonia concentration, when there is no nitrification, is in fact the ammonia concentration that would be available for nitrification if it could take place. And it is equal to the effluent ammonia concentration when nitrification does not take place. And by virtue of the structure of this equation, it is possible to have a higher effluent ammonia concentration than the measured influent concentration because of the production of ammonia from the biodegradable organic nitrogen. The effluent TKN concentration then would be the effluent ammonia concentration plus the unbiodegradable dissolved organic nitrogen, which would simply be equal to the influent TKN concentration minus that nitrogen concentration that is required for heterotrophic organism sludge production. If there is no nitrification, of course the nitrifier biomass would be zero, and the nitrification oxygen demand also would be zero. On the other hand, if the sludge age of the system is longer than the minimum for nitrification, then nitrification will take place. And the effluent ammonia concentration will be given by this equation that we derived for the effluent ammonia concentration, taking due account of the unaerated sludge mass fraction in the biological reactor. Now, notice this equation can give you negative results, because if the sludge age is very short, 1 upon the sludge age will be a big number. Add the endogenous respiration rate to that, then this term can be larger than that term, in which case the equation is negative. It is, of course, impossible. When that is the case, we must set the effluent ammonia concentration equal to that ammonia concentration available for nitrification for the non-nitrification case. Notice also that this equation can give you very high effluent ammonia concentrations in the order of hundreds of milligrams per liter. Because if the sludge age that we choose is, let's say, in a narrow range of like 5 or 6 days, then this value here is of approximately the same magnitude as that value there. But this one is larger than that one. The difference could be a very small positive number. Then the effluent ammonia concentration will be very high. It could be hundreds, thousands milligrams per liter. Clearly impossible. When that happens also, we must set the effluent ammonia concentration equal to the ammonia concentration available for nitrification for the non-nitrification situation I described earlier. But once the effluent ammonia concentration becomes less than the ammonia concentration I have available for nitrification, then we begin to get realistic effluent ammonia concentrations, and we keep the ammonia concentration. The effluent TKN concentration then would be that effluent ammonia concentration plus the unbiodegradable dissolved organic nitrogen. The nitrate concentration generated would be the ammonia concentration available for nitrification minus the residual ammonia concentration not nitrified, or that is equal to the influent TKN concentration minus the nitrogen that is required for sludge production for the heterotrophic organisms minus the effluent TKN. Then when we have our sludge age longer than the sludge age, of course, then nitrification occurs, and then analogous to the mass of ordinary heterotrophic organisms that we have in the reactor, the mass of ammonia nitrifying organisms is equal to the kilograms of nitrate generated, that's concentration of nitrate produced, times flow rate, gives kilograms of nitrate produced per day, times YRS over 1 plus BRS. And you notice that this term is identical to that of the ordinary heterotrophic organisms, except it has its own kinetic constants and stoichiometric constant. It has its own yield coefficient, the yield coefficient for nitrifying organisms, and it has its own endogenous respiration rate. So the flow rate times the nitrate concentration in the effluent is the mass of nitrate generated, which would be equal to the nitrate concentration in the effluent flow plus the nitrate concentration in the waste flow. And due to the water balance, the effluent flow plus the waste flow is equal to the influent flow. The nitrification oxygen demand would be the mass of nitrate generated times 4.57 milligrams of oxygen per milligram of nitrate generated.